Hey kiddos, hope you have enjoyed finding areas of rectangles and trapezoids in your effort to approximate area under a curve. So I'm going to draw a random squiggle wiggle. We're going to spend a little bit of time talking about why we care about areas under curves, and then we're going to spend some time doing a bunch of notation stuff to make our approximations better. So I drew a random squiggle. It's f of x. I'm going to start it here at A. I'm going to stop it here at B and say that that's the area I want to find. I want to approximate. Let's put some context in this one. Let's all make believe that this is a time axis that is measured in hours. And then let's pretend that this vertical axis is a rate of rainfall, because it's raining today, measured in inches per hour. So earlier this week, when you were chugging along finding areas of rectangles, and you found a rectangle that had a base and it had a height, if we come down here and just calculate based off of units, just do unit analysis here. So our base and our height, our base has units measured in hours. The height of that rectangle has units measured in inches per hour. And a quick crissy cross shows you that your output, when you find the area of a rectangle under a curve, is only measured in inches. So what you've done when you've calculated that area under a rate curve is you have undone the rate. You're undoing rates, which is super exciting. Maybe you don't know, but we have spent since July taking rates. We're taking derivatives. We're finding rates. And so now we're spending time undoing them. So you are undoing rates right now. That'll matter huge in about a week, but I just wanted to tell you why you're doing what you're doing. Okay, now for all the notation stuff. So let's zoom in here a little bit. Earlier this week, you were taking areas of rectangles and adding them up, and your rectangles were huge. I mean, they were huge. So the only way to get a better approximation is to use more partitions and to make skinnier, smaller, tinier rectangles. And I know you're groaning because you don't wanna, because it's more work. I'm gonna show you. You're gonna be fine. So now if I make smaller and smaller and smaller rectangles, the things that you already know are still true. So if I turn that distance and I look for in partitions, it's still going to be true that the width of each of our rectangles is going to be the distance you cover, b minus a, divided by the number of partitions you're taking. And, you know, the more partitions, the bigger the in value is, and so the smaller these are. Another way to call this is your change in x. I mean, of course it is. So we're going to start at A, we're going to move over something, and then we're going to move over another something, and then we're going to move over another something. Those are delta x's, those are change in x's. Okay, your height values are on your function. So they live here, and then here, and then here, and then here. Remembering that my goal is to make these tiny little slivers of rectangles. So these function values are going to be so close together. Like these are hugely far apart compared to what we're actually going to be doing. So if this is f of a, this one would be f of a plus delta x. The one next to it would be f of a plus 2 delta x as we move away 2 partitions, and then 3 partitions and 4 partitions, and we're going to do that for a while and for in partitions. So we're going to call that our heights. We're going to call their function values. They start at a, and we move away some number of partitions. I'm going to just call it delta x here. Please remember that delta x is b minus a over n. Don't think that it's something new. It's not something new. All right, so if I go find the area of a rectangle is still base times height. So I'm going to do my height first. Oops. Times delta x. That's the area of one rectangle. One rectangle is not enough, friends. So let's go add up a lot of rectangles. And let's start with the first rectangle, and we'll stop at the nth rectangle because we're doing n partitions. So if they wanted me to do 7, I could turn n into a 7 and plug 7s for all those n's, and that would be super fun. If they wanted me to do 95, I could plug 95 in for n, also super fun. Unfortunately, they're not going to ask for 7 or for 95. They're going to ask for infinity. So the other piece you need is a limit as n goes to infinity. Are you panicked? Don't panic. You're not actually taking a limit. Don't panic. It's just notation. So again, I just want to lay all the pieces out for you. This is the area of a rectangle. This lets you add up n rectangles. This lets you add up infinity rectangles. And that is the goal, because we are trying to find the exact area under the curve. Like, you are living in a world of approximations right now, which is super great. But if I take more and more and more tinier slivers, smaller, itsy bitsy little tiny rectangles in there, my approximation is going to get better and better and better. Okay, let me connect this to the notation you've seen in your Delta Maths, and that is this notation. Okay, I hope you've seen that before. A and B are the same A and B as before, your start and your stop. This super clean, simple symbol means all of this. It means take an infinite sum. So add sum infinitely, sum forever. Inside of it are rectangles. Here's your function values. Those are your heights of your rectangles. dx, remember the time we were saying change in y over change in x is your algebra, and now you're in calculus, we could use dy and dx. Same thing, this is your change in x. So everything matches, everything lines up. I'm going to erase this so that I can draw a bunch of arrows. This lines here, this lines here, and then your symbol lines, and your a and your b are the same. Okay, so you're going to need to be able to move fluidly from one notation to the other. And it's really strange to wrap your mind around the first couple ones you do, and then hopefully you start seeing that they're all kind of the same. They're all kind of the same. So for example, if I have this integral, I'm just going to make something up. It's going to be so wonderful. 6 to 12 is what I choose. The function I choose to use is inverse sine of x dx. I don't know. Chose it out of nowhere. I think it's going to be great. You have to go find two things in order to turn this. So what I'm doing is I'm going from the integral back into summation notation. You need two things. You need delta x, and you need your x's to plug into your function. Delta x is super fast because it's always the same. Delta x is b minus a over n, always. And you have to pull those from your integral symbol. So let's do that first. So if I go find delta x to be b minus a over n, b is 12, 6 is a, and it's n. It's just n because they didn't say in 7 rectangles or in 22 partitions. So it's just n. It's 6 over n. Your x's that you're going to put into your function is always a plus k delta x, always. Sometimes they use a different counter. Sometimes they use I instead of k, but it's just a counter in your summation notation. So if I do that here, our x's are going to be a, which is 6, plus k, it's just k, right, k. Delta x I already found, so here, let me rearrange it just a smidge. I'm going to do 6k over n. It's k times 6 over n, so 6k over n. These are your x's, friends. This is what x is. So when you do your function notation, that's what you're going to plug into your function. All right. When you do these in delta, delta is very friendly to you because they will already have this written. Let's see. They'll have this. They'll have this. They'll have this. written for you. And because that doesn't change, that never changes. You're always going to start with your first rectangle and go to your infinity rectangle as n goes to infinity. So they write that for you. So the part you have to write is this function now, but evaluated at your x's. So it's going to be, for us, inverse sine of 6 plus 6k over n. And I have to type that in. And then you have to type your dx, remembering that it's just delta x. And delta x is b minus a over n is 6 over n. And you'll type that in, and you'll press submit, and it'll give you the green check mark, and then you'll go do more. Okay, I also have assigned you a couple practicing going the other direction, so where they give you the summation notation and you have to write the integral. We will spend time in class going over those as well, but please get into Delta. Delta is so helpful for this stuff. All right, kids, let me know if you need anything.